Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here because today we are unpacking what is basically the holy grail of electric motor management. If you've ever wondered how modern electric vehicles or high-end industrial robots, or increasingly, even your household appliances get that incredibly smooth, precise, and super efficient movement, well, the secret is a brilliant engineering concept called field-oriented control.
Okay, let's dive right into our map for today. We'll start with making AC act like DC, look at the magic of transformations, compare direct versus indirect FOC, weigh censored against sensorless control, and finally, wrap up with exactly why FOC matters so much in our world today.
Section 1. Making AC act like DC. So here is the absolute million-dollar question. How on earth do we take a complex, chaotic AC motor and control it exactly like a simple, separately excited DC motor? You see, with a standard DC motor, control is wonderfully easy. The magnetic field flux and the armature current, which is what actually produces the torque, are completely independent of each other. You want more torque, you just pump more current into the armature. The magnetic field doesn't care, it isn't disturbed at all. But a three-phase AC induction or synchronous motor, oh, that is a totally different beast. You've got three alternating currents feeding into the stator, constantly shifting in time and space. The flux and the torque are just tangled together in this chaotic, sinusoidal mess. So how do we get that beautifully simple DC control in such an inherently complex AC machine?
The answer is field-oriented control, which you might also hear called vector control. At its core, FOC is a variable frequency drive control method. What it does is it takes those chaotic three-phase stator currents and identifies them as two completely separate orthogonal components. And the absolutely crucial magic word here is decoupled. By mathematically tearing the current apart into one vector that defines the magnetic flux and a perpendicular vector that defines the torque, FOC effectively tricks the AC motor into behaving exactly like that simple DC motor.
To really wrap your head around this, think about driving a car. Imagine if every single time you turned the steering wheel to the left, your engine's RPM suddenly spiked, and every time you turned right, your brakes slammed on, right? That coupled behavior would make driving a literal nightmare. That's exactly what trying to control an AC motor without FOC feels like. Adjusting the torque inherently messes with your magnetic field flux, but by decoupling them, we're essentially separating the engine from the steering wheel. We can demand massive, instant changes in torque, and the field flux linkage isn't affected even a tiny bit. This is what gives us that dynamic, lightning-fast torque response.
Section 2. The magic of transformations.
Now you're probably wondering, how do we actually pull off this decoupling? Well, the secret sauce is to convert the system of three-phase currents and voltages into a two-coordinate linear time invariant system. Basically, if you look at the raw data coming from an AC motor, the currents are oscillating wildly over time. Trying to control that directly takes a massive amount of computing power. But if we can use math to effectively freeze time, looking at the motor from the perspective of the spinning rotor itself, those crazy oscillating waves suddenly look like flat, steady DC lines. And once your inputs look like steady DC lines, you can just use simple, tried-and-true, proportional integral, or PI controllers to manage them.
We make this time-invariant state happen using a really clever two-step mathematical recipe. Step 1 is the Clarke's transformation. This takes our three-phase sinusoidal system, so phases A, B, and C, and projects them down into a two-phase stationary system, which we call alpha and beta. It just simplifies the geometry right off the bat. Then, step 2 is the real game changer, the Park transformation. The Park transform takes those two stationary axes and actively rotates them to perfectly match the spinning speed of the rotor's magnetic field. Because we're spinning our reference frame at the exact same speed as the motor, the AC signals appear to stand totally still. We're left with a direct axis for controlling field flux and a quadrature axis for controlling torque. Literally, chaos becomes order.
Section 3. Direct versus indirect FOC.
Okay, so we've got our direct and quadrature axes, but there are two distinct ways this control architecture is practically applied to AC drives, direct versus indirect FOC. Both methods want to control those axes, but they gather their vital intel differently. Direct field-oriented control, or DFOC, relies on a direct feedback model. It calculates the flux magnitude and angle using voltage or current models directly from the motor. On the flip side, indirect field-oriented control, or IFOC, uses a feed-forward approach. Instead of calculating the flux directly from those models, IFOC actually measures the stator currents and the rotor speed and then mathematically figures out the flux space angle by summing the rotor angle with a calculated slip angle.
So the crucial point here is that while both are totally viable, indirect FOC is overwhelmingly the top choice in modern closed-loop setups. And here's why. The direct calculation models used in DFOC can really struggle at extremely low speeds, mostly because the voltage signals get incredibly tiny and super hard to read accurately. But IFOC, because it uses feedforward and slip angle calculations, it effortlessly commands the motor across the entire speed range. I mean, from holding a heavy load at a dead stop at true zero speed, all the way up to high-speed field-weakening operations, IFOC is just rock solid.
Section 4. Sensored versus sensorless control.
Now, whether you're using direct or indirect methods, the microprocessors running the drive fundamentally still need to know exactly where the rotor is to line up those math transformations. And this perfectly illustrates a major trade-off in the industry: sensored versus sensorless control. Sensored, or closed-loop control, uses an actual physical mechanism, like a hardware encoder attached straight to the motor shaft, to feed the exact speed and position back to the drive. Because it has absolute, physical proof of the rotor's location, it can generate 100% full torque at absolute standstill, 0 Hz. It is the gold standard for ultimate dynamic accuracy in things like precision robotics. Sensorless control, however, totally ditches the fragile, expensive physical sensor. Instead, it relies on open-loop estimators and closed-loop observers. Basically, really clever algorithms that figure out the rotor's speed and position just by looking at the electrical voltage and currents. The key benefit? Massive cost savings and way better mechanical reliability, simply because there's no sensor to break. The catch is that these math-based estimators usually need a tiny bit of rotation to actually work accurately. That means they have a minimum speed limit of around 0.8 Hz before they can reliably guarantee full torque.
Section 5. Why FOC matters today. Let's move on and see how all this microscopic math translates into massive macroscopic real-world payoffs. FOC essentially guarantees ridiculously smooth operation across the entire speed range. You completely lose that jerky, inefficient behavior of older control methods. Plus, with closed-loop IFOC, you can generate full torque at 0 speed. Think about a crane holding a massive payload completely still in midair. That's FOC at work. And because the torque is decoupled, you unlock this jaw-dropping dynamic performance for lightning-fast acceleration and deceleration. But honestly, the biggest reason FOC is taking over everything from factory floors to washing machines is that it drives the motors so optimally, engineers can use much smaller, cheaper motors to do the exact same amount of work. Add in the vastly superior power consumption efficiency because you aren't wasting energy fighting the motor's internal magnetic coupling, and it's a total win-win.
Which leaves us with this final thought. Pulling off field-oriented control requires some serious processing muscle. But today, powerful digital signal processors, or DSPs, cost practically pennies. We literally have the computing power to crunch this complex math instantly and cheaply. So, as FOC continues to dramatically shrink motor sizes, slash power consumption, and boost performance, we have to ask, with the rising computational power of DSP microprocessors, will FOC universally displace traditional scalar V/F control everywhere? It certainly seems like the era of field-oriented control has well and truly arrived. Thanks so much for hanging out with me for this explainer. Keep learning, and I'll catch you on the next one.